Okay, so welcome to UCL's weekly radar seminar on Fridays at 2:30. Today we have Dr. Wenda Li presenting on the design of high-speed software-defined radar with GPU accelerated applications there. Wenda's been recently working on this, and I think it'll be of great interest to a number of people in the group that are using SDRs. So thank you, Wenda, for agreeing to give a presentation today, and over to you.
Okay, hi everyone. I'm Wenda Li. I'm a research fellow in UCL. Today I give the topic about the design of high-speed software-defined radar with GPU accelerator. So this is the content I'm going to present today. First, I give some introduction about the SDR radar and how my GPU accelerator is designed. And then I'll give some performance about this GPU acceleration. Then some future work I'll be say to how to further improve the speed of the GPU accelerator. So firstly, I give some very basic introduction about this software-defined radar. So basically, it's considered as a next generation for the radar platform. The principle is put all the single processing parts to be performed completely in software or basically just in the computer. And SDR radar is normally implemented by using the software-defined radio hardware. So software-defined radio is basically the way of the communication system they call this type of device. So SDR radar is using this SDR device here. The advantage of the SDR radar is it's very fast of development because all the single processing are in the software. So basically you can modify it very quick and easily, and it can be used for the multi-purpose operation. Again, because single processing is on the software. So if you change, for example, you change the you can sense in the Doppler, you can also sense in the angle. So that's up to how you design the system. And it also can give the real-time reconfiguration. So you can, when you write the code, you can just configure it very quick and run it on the SDR radar. So the SDR radar, the RF front of the SDR radar, including analog to digital conversion, ADC and DAC. Basically, this is to convert the digital signal to analog signal and transfer to the RF front from the computer. It also contains several of the RF mixer, amplifier, and filter. These are to maintain the bandwidth and the central carrier frequency for the SD radar. So here, this is the example of the architecture of the SDR device. So basically, you have the FPGA, including the DUC and the DCC. And then in the IF front, you have all the DAC and the LO and the amplifier and the filters, then connects to the antenna to receive signal. Then you will need a network link to transfer all the symbols, all the data captured by the SDR device and transfer to the computer, the client computer, which is the computing unit. And here, this is some example of the SDR device. For example, you can have this single channel, or you can have these 2 channels, and there are also some 4 channels. This USRP real here. And this is an overview of the SDR radar, the single processing here. So basically, what you do is you take the raw Wi-Fi signal from the SDR device, and then this is what you get. Then you put the you perform SD radar signal processing on the left view. You can get something like the Doppler spectrogram, or you can get this range angle plot to detect the relative angle from the signal source. Then when you get this Doppler spectrum and this angle information, you store it and pass to the for post processing. For example, you can use the MATLAB or the Python for multiple different of the applications. like this breathing detection, activity recognition, localization, people counting, and occupancy. All those machine learning tasks you can perform offline by using this other platform here. So what's the challenge in the SDRadar is, let's take the passive radar as an example. So basically, we are working on the wider of the bandwidth, start from the beginning of the FM radio as 50 kHz to 2 MHz. Then we have previously working on also this DVB signal, that's bandwidth about 2 MHz, bandwidth from 6 to 8 MHz. And then for the current Wi-Fi signal, it's about 20 MHz to at 2.4 GHz or 40 MHz at 5 GHz. And then for the future Wi-Fi signal, we are looking at something about 80 MHz and 1 to 160 MHz at 60 GHz frequency band. Also, we are having more of the channels here for passive radar. Currently, we need at least 2 channels, one for surveillance and one for reference. And this is the typical setup for passive radar. And then we are looking at something more like distributed receive nodes. So we want to have the surveillance channel at different of the angle. We are also looking at something like phased array radar. So basically, this is the MIMO radar. You're going to have a multiple of the receiver or transmitters. Also, we are the more complex algorithms. For example, those are super resolution algorithms like music and SAGE. So these are basically to search for the better resolution than the FFT. And we also and more complex algorithm for those multiple targets detection. So basically, you have more targets and more of the parameter calculation. So this will make the system become more complex. And then that's the challenge in the SDRadar. And here is the accelerator options here. So basically, we have there are the 4 main types of the accelerator can be used. Firstly is the CPU. This is the CPU is basically the general processor. It has a very high of the versatility. So basically, it's processing for everything. Therefore, it's slow at some functions because it's processing for everything. So it's not optimized for specific functions. Then otherwise, there's a second is can use the GPU. So GPU is basically they have a very strong power to do the parallel processing, but the GPU cannot replace the CPU because the GPU don't do some processing like data capture. That's still this part need to do in the CPU. Also, you can do some the acceleration by FPGA. So this is the reconfigurable circuit. It gives more flexibility than GPU. But FPGA is for every SDR device, you have to do the specific FPGA. So compared to the GPU, it's you can just develop one GPU accelerator that you can use for every different of the device. And there's one last method is to use the application-specific integrated circuit ASIC. So basically, this is the permanent circuit, and you cannot change anything of it. Although it gives you very high power efficient, but obviously we can use only for one thing. So that's something definitely not considered for the passive radar here. And here is the single processing in my SDRadar. So firstly, this is you get the raw IF signal from the SDR device, then perform a custom-indicated function, and then doing direct signal translation, and then do a CFAR to do the noise reduction. Then then you will get a Doppler range spectrogram. This is the typical way to process on the SDRadar. And this is the formula for the custom function. Again, this is just a classical formula here. And the basic idea of the GPU accelerator is if you think, look at this figure, this is the way of how the CPU process is doing a sequential processing here. So basically, it's do the processing one block by one block, and that's therefore it's the speed is not very fast. And if you processing the some FFT, for example, in the GPU, you will get much faster because the GPU do this parallel processing. So this obviously will give you much faster speed than the CPU here. And this is the design of how the SDRadar with the GPU accelerator. And so basically, in my design, I put it with 3 threads. Thread 1 is to capture the ROF data from the SDR device. So this is performed by the CPU. Then CPU will, when gets all those ROF data, it will prepare the data basically to retrieve the data, and then it will put into the host memory and upload to the GPU memory. Then the GPU memory, sorry, this is the GPU processing. Here, this will process a multi-channel cross-correlation by the GPU, and then the GPU will put the result back to the GPU memory and download to the CPU memory again. And then the CPU will do the post-processing over here. It will then to generate the spectrum, Doppler spectrum or range spectrum, and to give the result. And this is the in detail how the GPU implementation for the cross correlation. So so this the green box is the CPU process, and the red box is the GPU process. So firstly, when the SDRadar gets all the data here, the GPU process do a reshape on the data, and then download to the GPU, download by the GPU, and do all those capacity conjugate and the FFT and the multiplication and the IFFT. Then it will upload the data back to the CPU. Then CPU will do a final FFT on the across each of the block, each of the block to finish the cross correlation task. So by doing this, because all of this part are processed in GPU, so this will and this part is much faster than processing CPU. So this will give the advantage, make it the whole speed getting faster. And this is the coding example in LabVIEW to show how I design all the these 3 threads discussed before. So firstly, is have all the system initialization as this black red block. Then I take the do the USRP data DAQ from here. Then the update the data to the GPU accelerator to process the FFT, and then the final the data when it's getting, it will pass back to the CPU to do the post processing. And then just to show some performance for both the GPU and the CPU process. So here it's just taking a very simple of the 2D matrix of FFT process. In this A and C here, I keep the number of the batch that as number of blocks. Sorry, at 100. And here the in the B and D, I kept the length of the batch as 20K, and the total size matrix size for the processor, all the size is defined, and the number of blocks times multiplied by the times by the batch of the length of the batch. So as you can see, the GPU processing shows much better performance compared to the CPU processing, especially when this batch length increase is getting much better performance. And here is the acceleration ratio. It starts from about 2.5 times faster until 4.5 times faster when the batch length getting really long. And here it also shows when the parallel blocks increase, and GPU gives a much better, a much shorter of the processing time compared to the CPU. It's start from some 2.7 until 3.5 to compare speed fast quicker compared to the CPU process. Here I take some Wi-Fi data. I call Wi-Fi data from the measurement, and then I process the GPU and the CPU processing, and to show how this the frame rate of the Wi-Fi signal and the length of the batch effect on this cosmetic function. So on the first row, this is the cosmetic function calculated by the frame rate of 20. So let's see the frame rate by the Wi-Fi router. For the second row, this is by frame rate of 100, and for the third for the third row is by 1K of the frame rate. And for each row, each vertical here is by the different lengths of the batch, so from 10K until 200K, and therefore it can be very see when the batch length is increasing, this cosmetic function getting improves much better. Also, the frame rate will makes the overall performance getting much better when the frame rate is getting increased here. So this is the peak to signal to noise ratio against the batch length here. So you can see this PSNR keep increasing when the batch length increase as well here. And the red line here indicates the maximum CPU processing can achieve. So this is the so basically this can be think about the baseline for the CPU work, and this is the here is the performance gain by the GPU. If the GPU use the GPU accelerator to speed up the process, it can go up to 200K over here. And so basically overall, the GPU accelerator will give extra 3 to 7 dB performance gain on top of the CPU, on top of only the CPU processing here with exactly the same type of the algorithm. And here is a time spending to show how the exactly in each step of the GPU processing. So in here, first we take only the CPU process on USRP 2945 with 4 channels on 5 MHz, and then take another on the same bandwidth and use the GPU processing to do, and then take the GPU to run the full 20 MHz of the sampling rate. The batch length is kept for the 2 is 50K, and for the USRP for the 80 MHz is kept at 200K. So this will use the full sampling data from the sampling rate from the system. And as you can see, when you use only the CPU processing, you don't need to do this download to GPU or upload to GPU because you don't need to. It's all the signal processing are carried out by the CPU only. But however, you can see the CPU is doing very slow on the FFT and the IFFT, and the GPU gives a much better speed on the both FFT and the IFFT. So this, although GPU needs those download and upload time to transfer the data between CPU and the GPU, but this much faster processing on the IFFT makes the this extra time become very useful even to with those extra time. Additionally, overall, the CPU process takes 1.3 seconds to process this 1 second of data, yet GPU takes only 6.5 seconds to process the 1 second of data. So this obviously makes the GPU able to run in real time, where the CPU cannot run in real time here. And if we increase the batch length to 4 times than previously, this GPU have a similar processing time compared to the CPU. So both they are like 1.3 seconds here. So yeah. So here is an experiment setup for the real system to test with the GPU accelerator. And so here, firstly, we have a single source as the PLL as a FMCW single source, and we keep a transmitter over here, and then we have 3 receiver channels, and we have one receiver channels connects to the PLL to do just to the way like the passive radar, so we can capture the signal what it transmit and back to the system. So this is an example, the video to show how the system will be looks like. So just basically we'll do some working here. It will give some microdoppler signature on my body. So basically this is a very simple demonstration working forward and backwards, and some moving the legs, some like this. So basically you can see different of the signature because of the activity. And there are 3 spectrogram because there are 3 surveillance channel here. So this can gives you because currently they are put very closely together, so they give you basically the same of the Doppler signature. But when you can put the antenna into different angle, you will get receive different of the spectrum here. Because of using the GPU accelerator, so this is basically a 4-channel system processing at 20 megahertz. And here is just another demonstration about how this AOA detection can be used with this setup. So basically, when I working around this phased array antenna, I can be seen by the antenna with this strong beam, which is because of the signal reflect by my body. So it can be captured by the system here using this Wi-Fi signal. Okay, so here it's if this is the measured data, if we use a distributed channel to just the one shown before to measure the working. So you can see if we can measure it from different angle, this Doppler spectrum, this Doppler signature will show really big difference, even just the same activities. So this is so basically using this signature is going to be really helpful for those tasks like activity recognition or the people identification, things like this. To achieve such a performance, this is being enabled by the GPU accelerator. And some future work here is so first thing is going to make the current GPU accelerator with a higher efficiency. Basically, this is still just because of the coding. Feels like some coding is still not really efficiency. I think there are some rooms to make the GPU processing get even faster. And another one is to have the joint FPGA and the GPU accelerator design. Basically, because this USB will have FPGA there, and if somehow can use the FPGA to do some part of the pre-processing, that will be makes the whole system even faster than current system. And another change is the implement for 16-channel system using, for example, this called the digitizer net box ADC is provide a 16-channel of the synchronized 16 synchronized channel, coherent channel. So if we can perform some AOA detection or other detection on this system, is going to be really attractive solution, because this 16 channel for the passive radar is going to be really robust. Yeah, and that's my presentation for today. Thanks everyone.